Hello everyone, so in this problem we're going to calculate the integral of x times y dA, where a is the first quadrant of the graph of r equivalent to sine of 2 theta. So to do this problem we want to substitute x and y into r and theta. So x equals to r cosine theta and y equals to r sine theta. And the Jacobian for substituting the coordinate system would be r. So the original surface integral, which is x times y times dA, would be just the integral of r cosine theta times r sine theta times the Jacobian r times dr d theta. And r is from 0 to sine of 2 theta. And since it is in the first quadrant, theta is from 0 to pi over 2. So we can sort this out to get the integral of 1/2 of r to the third times sine of 2 theta times dr times d theta. And r is from 0 to sine of 2 theta, and theta is from 0 to pi over 2. Now, notice that in the first integral, we have this cosine theta times sine theta. And from the hint, we see that it is just 1/2 of sine of 2 theta. So we can change it into this part. So we can see that this integral can be separated into 3 parts. The first part is a constant, it is 1/2. And the second part is sine of 2 theta. And the third part is r to the third. So we can separate this integral into 3 parts, and it will make this integral to be much easier. So after evaluating it, it becomes 1/2 of the integral of 1/4 times, well, because r is from 0 to sine of 2 theta, it is sine to the power of 4 of 2 theta times sine of 2 theta times d theta, and theta is from 0 to pi over 2. So first of all, let's take this 1/4 outside of the integration, so it becomes 1/8 of sine to the power of 5 of 2 theta times d theta, and theta is from 0 to pi over 2. Now, how do we deal with this integral? We can see that sine to the power of 5 of 2 theta can be written as sine of 2 theta times the square of sine of 2 theta times the square of sine of 2 theta. Now, the square of sine of 2 theta can be written as 1 minus the square of cosine 2 theta. And the derivative of cosine 2 theta is just sine of 2 theta times 2. So in our original formula, we have sine to the power of 5 of 2 theta. And we can substitute that with the 1 minus cosine squared 2 theta. So it becomes the integral of negative 1/2 of the square of 1 minus cosine squared 2 theta, the cosine 2 theta. Now, because there's all these cosine 2 thetas going around in this integral, so I really want to change the variables right here. So let's make u as our cosine 2 theta. So du is equivalent to d cosine 2 theta. And when theta equals to pi over 2, u is equivalent to -1. And then when theta equals to 0, u is equivalent to 1. Now, this integral can be written as 1/8 of the integral of -1/2 times 1 minus u squared times du, and u is from 1 to -1. Now, we want the upper bound to be larger than the lower bound, so we can swap that and add back a negation. So this integral becomes 1/16 times the integral of the square of 1 minus u squared times du, and u is from -1 to 1. So this integral should be quite straightforward. We can first expand this square of 1 minus u squared, so it becomes 1 minus 2 times u squared plus u to the 4th. And u is from -1 to 1. Well, u is from 1 to -1 because when theta equals to 0, cosine 2 theta equals to 1. And when theta equals to pi over 2, cosine 2 theta is cosine pi, and it is -1. So there, that is the reason for the upper bound and the lower bound of u. So anyways, we have this integral, which is 1/16 times the integral of 1 minus 2 times u squared plus u to the 4th times du. And u is from -1 to 1. So this one should be quite straightforward to evaluate. It is just 1/16 times u minus 2/3 times u to the 3rd plus 1/5 times u to the 5th. And u is from -1 to 1. So let's substitute u with 1 and -1. So the answer is just 1 over 16 times 8 over 15 plus 8 over 15. So in the brackets, it is actually 16 over 15. And multiplying it with 1 over 16, it becomes, well, just 1 over 15. And that is the answer of this problem.